Okay. Start in a minute. Just wait for several more people to arrive. Everybody seeing what I have on the screen?
Yes.
Okay. Thanks, Galib. Okay, so since I'm sharing full screen, I don't see your questions. So if you have questions at any point in time, simply stop me and ask questions. So before I start, welcome. I start this weekly or bi-weekly presentation in order to broadcast the knowledge that we have inside our group and not keep it to ourselves. I thought that a proper topic today would be to start with the PBR, because PBR is such a hot word or hot topic. And so whenever you encounter graphics these days, probably the first sentence will be about PBR and what's the innovations there. And really what it means is physically based rendering or physically based shading. So PBR and BRDF, we will speak about this today, and I will unveil a bit of the background for that. Usually I used to give this as a presentation, which is 2 to 3 hours. Today we have 1 hour. So unless you'll tell me that you want to dive into the nitty gritty and then we'll do it over 2 presentations, I rather keep it relatively simple, because the audience that we have today is a broad audience. I don't want to get too down deep into the math equations, but I want to everybody after this presentation to basically take the understanding what is PBR, why is PBR good, what was the change in the industry, etc. All the material that I present today is accurate, although there's minimum amount of accuracies that just got there for simplicity. The technology described there is mainly correct until 2016. After that, or 2015, after that, some more things were added just to complicate the model a bit more, so we won't get into that. So without further ado, I will start. So I will start by going over the base lighting, or the simplified lighting model that existed for probably like 30 years in computer graphics, just because the graphics were not programmable or we didn't have enough power. And so we simplified everything, and we called the 3 components of the lighting ambient, or GI, global illumination. When you hear GI, you know that, diffuse and specular. And so in general, the GI, global illumination, is all the energy that gets to us indirectly from the environment. So the environment itself is lit by many light sources, and then materials in the environment, each one of them has a color that we see it. That color means that this is the wavelength that the material actually emits back into the environment. And so we have energy keep going between objects until it reaches equilibrium. So this energy that goes between the objects, so it's indirect lighting sources, is the global illumination, is the ambient, what we used to call it. And an example for that can be if you look under the table, and the table is under the table is not directly lit, you put your hand and your head is not completely black, which means that there is energy that coming from all kind of directions, but it's not directly lit. The next energy type is diffuse. And diffuse is basically means that energy comes from a light source, but it is reflected. The energy that is not being absorbed by the object is reflected equally along the entire hemisphere of the surface. Finally, we have specular, and specular is actually a lobe which is reflected towards the eyes of the viewer. So each type of material might have a different lobe according to the reflectancy, metallicness, etc. And so when we look at a material, the amount of energy that is reflected from the light in the reflectance direction where it meets the eye, this is the specular component. And as you can see, at the early days, we did these equations where we took all of the light sources and we summed them up as a simple dot product. Dot product is the cosine, and the cosine there is because we actually want to normalize the lighting. So really, lighting at 90 degrees, you get 100%. When it has a bit of an angle, you need to account for that. You can think about it as a spread on the area. And the same we did for the specular, only the specular we add some power that represented the reflectiveness, and we added some artificial coefficients which represented the ambient, which is the global illumination. So that was the initial days, and that started to change in the industry around 2008 or 2010, and in the game industry, the change really started 2012 to 15, where today all of the game industry is really PBR driven. Even the film industry only took that step between 2005 to 2008. Before that, they were using just simplified equations or full tracing, which took hours and hours and days to render frame. Okay, so here we're starting to get into what is a PBR, and in order to explore that, we need to learn about a new creature which is called BRDF. BRDF is a bidirectional reflectance distribution function. And what it means is basically there is a ratio that we would like to acquire. This is a function which represent the energy that is incoming. This represented by two different angles. To the energy that is emitted at a certain direction, also two angles, and an additional angle towards the surface itself. So basically, it's a function with 5 coefficients, and we won't get into that function. But what we would like to see is that we can represent this by basically FLV, and this is the coefficient that we're looking for. And this coefficient is basically some sort of ratio between the incoming light and the outgoing ray that we're looking into. And this is very important because basically we will start with the reflectance into our eye, and we will try to understand how to get to that energy, and according to which we will try to understand how is the energy distribution can be computed. Now, the problem with the previous slide, with the previous simplified version, is the fact that the artist can control what is the KD, what is the coefficient for the diffuse part, for the ambient part, and for the specular part. And they did that per material in order for the material to look good enough. But that means that each material interacted with the energy, with the actual energy in the scene, totally different. And so with different angles and scene that combined with many materials, things needed a lot of tweaking in order to look correct. Basically, the energy was broken because there's nothing here that guarantees that energy is not too much energy, so more energy is overflowing to the eye than what it should, or too little. So I'll stop here for a second and ask if there's any questions so far. Okay, so moving on. Basically, FLV, the function which represent what is the relation between incoming energy from a direction to an outgoing energy in a certain direction, is simply the ratio as it is here, DLR divided by DLI, but divided by cosine. The division by cosine is quite simple. Again, the same explanation says that the energy that is coming to the surface, it has a certain angle, and the distribution on the area or the coverage of the area is such that it depends on the cosine. So obviously, this is why the cosine. And if we're doing a sum of all of these energy, we will get to something which is between 0 and the total energy that we started with. Okay, so this sum is a way to do it, for example, with rays, but basically it should be an integral. And you see the integral here below. Excuse me. Okay, so let's just talk about energy conservation for a second. What we want to say is basically that the amount of energy that is outgoing is smaller than the amount of energy that is incoming, and it's greater than zero. Or in other words, we have this integral that is exactly that ratio, FLV, and if we do the integral over the hemisphere, dot the cosine time the cosine, it's between 0 and 1, which is quite obvious. Okay, so let's define this reflection function or reflectance function. Basically, the reflectance function, the FLV is this. We'll call it Ri now. And if we look at the diffuse, we can actually kind of get to it really easily. Because if you look at this integral here, which is basically integral over the half hemisphere and time the cosine, we know that what's representing diffuse, if you remember the very first slide, diffuse is uniform across all directions. So in this case, what we can say is, since it's uniform on all directions, then we can do the integral over the cosine, and FLV is just a constant. So we need to find a constant. And if we look at this, the constant, if you do the integral, is really pi. And so what we need to do is simply take the color of the material, the ambient, the way that we call it, ambient or diffuse, and divide by pi, and that's it. That's the energy of the diffuse that we need to do. So that's relatively easy, and it's very nicely plugged in. By the way, just a word of caution, we still did not say that this is the full energy that we'll get from a material, because obviously there's the energy for the specular and the energy of the diffuse. The specular is the lobe and the diffuse is the homogeneous distribution. And so we will need to find what is the relation between the specular and the diffuse. And so now we are getting into the Frenet. And the Frenet is exactly what I said. We need to understand the amount of energy that we're going to spend, or that the energy that is spent towards the specular lobe, and the amount of energy that is left that is spent towards the diffuse lobe. Because after all, it's a unified lobe, which is partially homogeneous and partially is combined out of the specular at a certain direction. And so for that, we can use something which is called the Snell law. And the Snell law is basically saying when two medias are coming together, there's an interaction when you look at the way that ray is refracted and reflected. And it's easy to describe by N1 divided by N2 equals cosine 2 divided by cosine 1. So we won't get into it, just accept it. You probably learn it in high school. But basically, using the Snell law, we can start to navigate toward a way more complex equation, which is the Frenet. And the Frenet is saying, okay, what is the amount of energy that is refracted from a surface giving a certain angle? So using those N1 and N2, N1 and N2, by the way, are the coefficients of each material, okay, coefficient of refraction, or index of refraction, that's how they call. And so using these two factors, we can decide, and based on the angle, we can decide what is the amount of energy that will be reflected from the surface. Okay, because there are two energies that we are interested in. We have when an energy comes to a surface, what happens is that part of the energy, according to the grazing angle, will be reflected, and the other one will be partially absorbed. It penetrates the surface. So whatever was reflected does not penetrate the surface. It just grazed off. But the rest of the energy penetrates the surface, and now, according to the parameters of the material, it will partially be diffused. In other words, reflected in a homogeneous way. And the other part will be absorbed. Okay, so for this Frenet equation, there's an approximation which is called Schlick, but it doesn't really matter. And it means basically this. if you give me a certain number, which we call F0, and F0 is a parameter which every material has. F0 basically means how reflected are you? And in the next slide, I'll show that. I can do some magic using the angle of the incoming light and the angles towards the eye. I can do some magic and I can decide what is the fraction of energy that should go to the reflected part. In other words, I can tell you how much of the energy will be towards the specular lobe. And this is a very important formula, by the way, the Schlick formula, because it's a really fast approximation of a very complex Frenet formula. Okay, so real fast, this is a demonstration of different materials. What this graph shows is how the angle, you can see that 0 to 90. So given an angle, how will the energy reflected behave? So you can see, for example, I'm looking at water. Water is the blue. It's a very bottom curve. So you see that water, for example, is really flat. It's around 0.02. That's the F0 coefficient, meaning that we started reflectance angle at 0, 10, 20, 30. We're getting all the way to grazing angle of around 60%, or 60 degrees, excuse me, and we have no energy going to reflectance. So we basically see through the water. Okay, but around 60 degrees, 50 to 60 degrees, some very unusual phenomena starts to happen. And we see that the graph, the curve goes really up. And at 90 degrees, it goes all the way to 1. That means that at grazing angle, when we look at water, we actually see a perfect mirror reflection. Okay, so that is really interesting things to notice. That means that, and I can tell you that almost for a fact for, let's say, 95 to 99% of the materials, if you look at almost any material between 80 to 90 degrees, you're looking, your view direction is 80 to 90 degrees to the surface of that material. And try this at home. Look, even at wood or even at your wall at home, you will see a reflection. You will see a reflection with low energy, but you will see a reflection of what's reflected at the 10 degrees, let's say, or 5 degrees from that angle that you're looking. So this explains a lot of phenomena that we see in nature. One of them is the water reflection, that when you see up close at not a grazing angle, but really a shallow angle, a deep angle, you see through the water. But at shallow angle, you actually see a perfect reflection. This explains how you can see, almost explain how you can see off asphalt when there's a bit of water vapors on the asphalt. This explains how you can stand in a bus, and I tried that actually. You look at the plastic that covers the bus, and when you passes 60 degrees, you actually start to see reflections. So try that at home. It's really interesting to see. Okay, but if we go further than that, let's look at some interesting other materials. You will see in red copper. So you'll notice that copper starts actually around 0.55, 0.65. Okay, so this is interesting. It's not a single reflection. It's not a single F0 curve. It has several. In fact, it has, well, we call it 3 because we measure with RGB, red, green, and blue. And so each one of the components will have a different F0, which is really, really an interesting result. And so, for example, gold will reflect itself, will behave, and will give you the comprehension that the color is really around orange. And so this is really the explanation for that. Unfortunately, not all the metal materials behaves really nicely. And you can see that some of them, for example, aluminum, has a bit of a dip below, which is really surprising, by the way, a really dip below around 70 to 80 degrees, and then it goes up. But for our approximation, let's just say that the model of Schlick is good enough. Okay, I'll stop here, and I will ask if there's any questions here.
I have a question, actually. So how
Yeah.
was this graph created? Is this mostly a simulation or like actual physics?
Okay, so that graph is actually a real physics. In order to represent this graph, a lot of researchers actually took materials and they actually measured the energy reflectance of materials. They actually simulated a complete vacuum and perfect laboratory conditions, and they measured that. And so all of these graphs are heavily relied on a priori scientific data that was gathered. Unlike, by the way, the Schlick. Schlick is just an approximation. It's a curve that will try to imitate, given f0, meaning giving a starting point which is between 0 to 1, how will the graph try to correlate the curve? This is just an approximation. If you actually want the real formulation, you go to the Frenet formulation, which is much heavier. Okay, other questions? Okay, now Anton mentioned that the lack of diffuse just means that none of the light that is absorbed gets scattered back out. That is true, meaning that if you have such a grazing angle that the specular energy came at an angle that is totally reflected, think about it this way, it is bounced off the surface. If an energy is bounced off the surface, none of it is getting absorbed and none of this is getting to the surface itself or to under the surface, actually, to the media. And so there is no diffuse part. So as the specular part go up, automatically the energy spent in the diffuse must go down, because in total, the sum of both specular and diffuse must meet at maximum the amount of energy that you put into it. Okay, so just last word about the F0. The F0 is very, very important, and it can represent actually the type of material. In nature, we identified mainly two groups of material. One of them is called the electric, and the other one is called metallic. And these groups are very different. Most dielectric or all dielectric materials in nature, you can see that their F0 will be no greater than 0.05. In fact, the average will be 0.02 to 0.04. F0, that means the reflectance at zero angle, meaning 90 degrees look down. In contrast, the metallic F0, all the metallic materials will be way higher. Will start at 0.54, I think it's the lowest, but usually it will be around the 0.7 and 0.9. So that means that their reflectance is mainly based on simply reflection of the energy without any absorption, almost with no diffuse component. So that's extremely important to understand. There are some materials in between, such as, I think, diamond. Diamond sits roughly around 0.16, etc., but it doesn't really interest us at this point. So what we can do in computer graphics is actually give a lever or a texture that can control how metallic is a pixel or how metallic is an entire material. And according to this lever, we can control the appearance and the behavior of the energy. Okay, so I'm moving on. Let's see. Johnny said, most artists want to simplify the understanding. Currently, the workflow is PBR use 0.4 float. Oh, you mean for the dielectric? Yes. Okay, so moving forward, we're still missing an understanding how to use this reflection because, frankly, we're talking about reflectance, and clearly when we're looking at an object, the light source will not be exactly at the reflection lobe from the eye. So that's a problem. But actually, it's not exactly right. It will be in the reflection lobe. It will simply not be in the reflection center, meaning that if we use the normal of the surface and we compute now the vector, we are not at the center of the reflected vector. So how do we compute the amount of energy then? Okay, so a really nice technique, and this is where we start to connect the PBR theory or the BRDF theory to everything we do today came up several years ago, or 15 years ago, 20 years ago, and this is called the microfacet theory. Microfacet theory actually say, hey, surfaces are actually do not contain a single normal for the entire surface. Really, a surface is combined of many microfacets. So let's say we have a normalized distribution of the normal. And by the way, this is not correct. This is correct for 95% of the material, but we have exceptions, and we will not discuss this at this point in time. We can touch it maybe at the end of the presentation. And so, given that we have a normal distribution of normal on the surface, you can say that no matter where the viewer is and when the light is, we always have a microfacet normal that is exactly center between the incoming vector and the outgoing vector to the eye, meaning that normal is that light ongoing to the eye is exactly reflection. So the only thing missing here is now to calculate, okay, so what is the probability of such normal, or what is the amount of the overall normal in these points to be along this direction? And this is really what interests us. This is exactly directly connected to what we call the normal distribution function. So if we know that, we can say, okay, let's say that 0.25% of the normals in this location will be exactly at the right direction so that the light will be reflected to our eyes. Then we take the entire energy. We said, take the entire energy, multiply by 0.25, and this is the amount of energy that is actually reflected as a specular. So that's great. That's what we actually try to do. We still have some missing points there. This is fine if the surface is totally flat, but since we are now having microfacets, the surface is not flat anymore. That means that we have something which is called shadowing and masking. So a light on the way might be occluded by some of the subsurfaces along the way, and so it will not hit the point. Or let's say that it hit the point, now it's reflected towards the eye, but it is blocked from the eye because it's concealed on the way to the eye. And so shadowing and masking. So we need to account for the probability of the eye and the light being occluded as well. And so for that, we have the geometry distribution function. So we're already talking about two functions. One is the normal distribution function. The other one is the geometry distribution function for occlusion. And lastly, we already spoke about the Frenet function, which we said we will use the Schlick. And so if we put everything together, we get the BRDF equation. Great. I mean, we started with something which was so complex we didn't even want to get to an equation, but now it's really simple because the BRDF for a ray coming from the light, which represented by L, the direction, and outgoing towards the eye, which represented by V, can now be represented by, let's see, the Frenet coefficient times the shadowing coefficient or probability times the normal distribution probability. And all of this we divide by 4 cosine and cosine. And the reason for that is if you do the hemisphere integration, you need to have these terms in order to basically divide by the 2 cosines. So that is great. I don't know if you understood how far we got here, but you should tap yourself on the shoulder because basically we now can say, okay, this is the amount of energy given the direction of the light, and I know where the eye is located, I can now say how much light will be reflected. So I know how to calculate the specular component. This is huge. Okay. Any questions until now? No questions. Okay, so I'll move on. So we did not speak about, or we did not explain about the diffuse. The diffuse, the only thing that we said, okay, we know what would be the distribution of the diffuse, and it's a constant. We show that it's basically the albedo coefficient of the material divided by pi, just because of the hemisphere integration. And so now that we know the amount of energy that I'm going to spend because of the specular, can I know what is the energy for the diffuse at that specific direction of both Li and I? And the answer is actually yes. Since we already calculated the Frenet, if we take 1 minus the Frenet, that is the portion that is left for energy which was absorbed, which penetrated the surface and can now be partially absorbed and partly emitted as the diffuse component. So this is amazing. I mean, we just revealed the fact that we know how to calculate in an energy conservative way the entire lighting equation. Okay, so let's see what I wrote here just to make sure that I did not forget anything. Okay, how do we refer to roughness then? Because up until now, I refer to specular and diffuse, and we know that specular used to be tied with some exponent, and basically we call this exponent today roughness or smoothness. One is one minus the other or correlated to it. And so roughness will say, if the surface is extremely rough, then we're getting that with full roughness, I would expect the lobe of the specular to be almost as wide as the lobe of the diffuse. Does that make sense? Meaning that if the roughness is so high that the surface is all uniformly distributing to every direction, then a specular will simply shoot towards every direction possible. The lobe will be so wide that there is no significant almost to the direction of the incoming light and the eye. Does that make sense? Okay, on the other end, if the roughness is really, really low, then we have a lobe which is basically a spike, a delta spike. And that's exactly what we described here. So the way to accommodate for that is to actually plug the roughness into two of the components that we looked at. Oh, well, actually three. One will be the Schlick. Why the Schlick? Because we need to accommodate for the fact that now we're not referring to a single angle, but really it's a range of angles. And so the Schlick. The other one will be the normal distribution, because the normal distribution, as you're becoming from a spike into something wider, we will need to change the distribution to affect it. And obviously the geometry will be also affected. So we covered roughness. I will not show you how we covered that, but if you plug it into the equation, there should be a way to compensate going between the two ranges. Okay, there is a remark here also. So far we talked about uniform distribution of diffuse, obviously, but also for specular. So it doesn't matter really if the angle is coming 30% towards the normal, it doesn't really matter what the angle towards the angle. When you look, you can take a normal and then rotate around it 360 degrees on the surface itself. We did not take this into account. We said it doesn't matter, we can rotate and there's no effect. All the surface is pretty much homogeneous to that reflectance. But that assumption is not correct for roughly 5 to 10% of the materials in nature. And so we will not touch it, but we'll just say that when we're talking about that, we can in the future say, okay, I know that this is an isotropic material response, meaning that it does not correlate any direction the same way. And it should be pretty easy to just tweak into these distribution functions and say, okay, different directions will affect that distribution function a bit differently. Okay. What about energy conservation? We spoke about this indirectly, but I will just go over that. So we just discovered that doing what we did with the Frenet, specular plus diffuse will always be, actually it should have been smaller or equal to the total energy. Okay, so there's a miss there in the slide. What else? Specular portion, as I said, is resemblance to the Frenet at the angle, while the diffuse is whatever is remained. So it will be 1 minus the Frenet. Now, is that accurate? Let's see. There's a question there, which is basically saying, okay, you remember the geometry function that we encountered before? The geometry function was all about shadowing from the ray, from the light to the surface, and from the surface to the eye, right? It's a double function. And so this energy, what happens to this energy? I mean, this energy is not a specular anymore because we cannot assume that it went towards the direction of the specular. But if it's not specular anymore, then it must be something else. It's not simply disappearing. And so that's something pretty nice that the film industry discovered around not actually that long ago, I think 2012 or 14, something like this. And Sony Studio came up with a solution, and they said, hey, that's actually simple, because take whatever was occluded there, and you can add it, or at least half of it, you can add to the diffuse portion, because in a way, now it penetrated the surface, and now it should go through a diffuse reaction. So that's really important to remember, because all of a sudden, if you add that amount of energy, you see that the object looks lit more correctly. Otherwise, this energy disappeared. It was not correct. Okay, moving on. So how do we handle the GI? Because up until now, we spoke about what we call analytic lights, meaning we touched all the lights which are directly lit. But now we're talking about the environment. So what do we do there? So I will start with a simple example, which is what most of the game industry, around 99% of the time, is still doing. And this is basically using what we call environment maps. So what is an environment map? Environment map is a location within the game where we are baking basically a cube map or a sphere map, where we're capture the entire lit, and this is important, we're capturing the entire lit environment around us. So that's really important, because by capturing the lit environment around us, that means that we're actually capturing the energy that is flowing through that point in space. This is how this point in space see the environment, meaning see, that means that a photon from each one of the pixels is reaching this point in space, and this is the amount of energy gathered there. In other words, we actually are talking now about what we call GI, or global illumination. So a word of caution about that, that is not exactly right. The reason this is not exactly right, because what I just described is actually a reflection map. And a reflection map means that if I now put an object and I will reflect a ray from the eye, I can now reflect a ray towards this environment map at that direction. And if I pick the pixel in this environment map that represent it, I will get the actual specular reflection, because this is reflection. Okay, so it's not exactly GI, it's actually reflection from the environment, which, by the way, we're missing, because up until now we did reflection from the lights, but not from the environment. So this part is still missing. And how do we add it? We simply add it. We do not account towards any of the energy that we accumulated so far, because it is additive. It's fully additive from the environment. Okay, but that's not exactly right, because this is, we said this is the specular. What about the equivalent diffuse? Okay, the equivalent diffuse is actually, what if we take this environment map, and what we want to explore really is, if I take a surface at a certain point and I'm saying this surface as a normal pointing towards a certain direction, what I want to say is basically how much energy do I get from the entire environment over that point? Or in other words, I need to integrate the entire environment over the entire semi-hemisphere, or excuse me, the entire hemisphere in that point in space. So this is really interesting and sounds really, really complex. But really what I'm saying is, how much energy do I get from the environment at a point in space where I know that this point is on a surface, so I'm getting only half space, the hemisphere. Okay, so the way to do it is to say, okay, let's say that I'm taking the normal of that point on the surface, and I'm sampling the same cube map. Only if I sample that cube map, I'm sampling a point in the cube map, and I actually want to sample the entire integration. So it's easy. Take the cube map, and for each pixel on the cube map, you now need to do integration over half the cube map, but in a smart way, because it's actually integration over hemisphere, not over a box. So you need to do an integration over the cube map and get into that pixel. The new pixel will represent the integration of energy divided by 2 pi. Why 2 pi? Because obviously that's when you do an integration over hemisphere. Okay, so this actually is the accurate way to get what we call GI maps or diffuse maps. Okay, so now the only thing left to do is to decide how do we combine the GI energy. And the GI energy integration is exactly the same like we did before with the analytic light. Meaning, what we'll do is we will take a ray, we will shoot it towards the surface, we will reflect, but this time we don't need to have all of these subsurface scatter, all of these, microfacets theory. We actually use the normal. We reflect and we take, according to the Frenet, we take the portion of the light, the portion of the energy that comes from the pixel of the environment map. Now, 1 minus that portion, meaning 1 minus the Frenet at that direction, will be the portion of the GI energy that we want to get from the environment, not from the lights. The lights we already got. And so we take this portion and we multiply it by what? We take the direction of the normal and we sample what is the portion along the hemisphere of the energy integration from that cube map. And by doing that, we now also got the GI, which is comprises of both specular part and diffuse part. So now take what we got on the GI part, take what we got from the direct analytic light, combine them together, and we have the full energy that object, that point on surface should get. And this is really, really the full equation and the full understanding of what's going on without getting into details of special materials and special reflection, etc. Now, obviously, if you choose to replace the environment map with ray shooting, you can do that. So instead of sampling 1 pixel on the ENV map, you're actually shooting a ray or several rays towards a reflection direction and take actual ray tracing. That's totally possible. And along the diffuse, you actually multi-sample a lot of pixels in random direction. And as you increase the amount of rays, you get better accuracy. Totally feasible. That is what the film industry is actually doing. And in order to use minimal amount of lights, they call something which is called denoising. They're called a AI process, which is doing denoising in order to get a good approximation, which is close to the, let's say that instead of sending 1 million rays, you'll send 100 rays, you'll get good enough results. Let's say 99% of the energy should be accurate. And so I think that this is most of the theory that I wanted to go through today. And maybe now we'll have some questions and then I'll show you a quick demo. Let's just see. Okay, I'll go over the next graph and then I'll open for questions. Let's see what I forgot. So, yes, I did forget something. What do we do about high roughness when we get to the GI? So this is a good question because when we get to the GI component, high roughness will be a high lobe or high angle, wide angle lobe when it comes to the reflection one. And so what we can do if we're using environment map, we can actually use lower MIP map. So we're actually sampling the environment map, but what we're doing, we're downsampling them to several levels, and each level is more blurry, representing the energy that we'll get from several neighbor pixels in this environment. And so if we downsample, but we need to be careful, we need to downsample in a way which preserve the actually the angle, and that's not that easy to do. If we downsample and preserve the angle, the solid angle, then we can use a lower MIP and get the effect. And obviously the smart ones will automatically say, okay, but if we're close to the horizon, then we're sampling something which is below the horizon, and you're absolutely correct. We need to correct that as well. Okay, and the same goes to the specular map. What happens when we have high RAF and we're sampling the environment map for specular? Again, we will use lower MIP and get the same result. And again, we'll need to be careful about going below the horizon and cutting the energy, so we won't get below the horizon over energy, and also we won't get interference from, for example, red light, which is under the horizon, but you actually put it in your sampling. How about discuss metal rough? That's Chris. How about discuss metal rough versus spec gloss workflow? If you don't mind, I actually don't want to get into, okay, why not? I'll mention it in a word. So metal rough is PBR. The way that PBR developed, we started with the understanding of, ambient, diffuse, and specular. And so obviously the pipeline was more towards what is specular and glossiness. Now, as we moved into PBR, we actually says, well, it's way easier and way more natural for us to work with the definition of metallicness. So metallicness will simply control how metallic an object is. And then roughness will control how much shine, how much reflectance, or how spiky the lobe of the specular is. The transition between, for example, glossiness and roughness, most of the time is 1 minus roughness will be the glossiness, or squares, or 1 minus square, something like this. And so it's really an easy transition. To go between specular to metallicness, I don't want to go into details there, because in order to understand the question, you need to be an artist, really. But it's important to understand that when we're going from, for example, what used to be specular into metallicness, or PBR, the way that we work today, as the metallicness go high, we need to basically say that the albedo component, meaning the undersurface, the media reflectance, is going towards black. Why? It's kind of obvious, because we said that when we're dealing with metallic objects, then most of the energy is reflected back, and it's reflected according to RGB channels, meaning RGB frequencies actually, that will determine if it's uniform or part of it will be actually absorbed. Okay, and so if the metallic value is really high, that means that we didn't really use almost any diffuse. And so it's as if we're saying that the albedo went into black, and really we're using what is the F0 coefficients. So that's how much I want to touch it. I don't want to get more into that. What else do we have? Okay, so I think that now I will just show you the next slide. And the next slide shows you basically examples of what happens if you go, that's metallic with low RAF. That's the top left head. That's metallic with, high RAF. Here you see that the roughness was reduced, so it's more spiky, and it's still metallicness with some rust. And here you see that the metallicness, actually, we took the metallic down, and so it looks more like either bronze or maybe even marble. Same goes here. If you look at the center image, the center head, you'll see how with a single texture, and this is the beauty of PBR, you can control stuff like metallicness, roughness, etc. through texture. So this is amazing, because you just specify a texture and look through texture, the same head, look how the same head looks so very different, and automatically your brain connects that to being metallic or not metallic and the amount of reflectance. And so if you look at the center head, you will see that you can clearly identify that there are paint stripes going over the head, but the head itself is something like metallic chrome. And so this is the beauty. And look below, bottom left, you see that although it's a lot about metallic, etc., you can also define organic material, such as combination between leaves, mud, etc. And all of this just by defining the texture and the response to clear coat, to roughness, and to metallicness. And so look how just by defining texture, you can create something as elaborate as ground texture, which comprises of many materials. Okay, so let's see. Let's go over some of the questions, or maybe you can raise hands and we will get some questions. So if you want to ask a question, how about raise hands and we will. Yes, I see that there's a discussion about cloth. So as I mentioned, there are some materials which are the exceptions, which are somewhere around the 5% of materials are exceptions. They are not reflected in a way which is equivalent along the entire surface, meaning that if you change the rotation around the surface, you get different reflectance. And also the equation that we described will need to use different type of laws. The Schlick approximation is not correct towards these materials. So we need to touch base two things. A, the anisotropic. Up until now, we assume that everything is homogenic isotropic. We need to assume differently. And so the rotation of the angle of the incoming light and the eye around the normal will change the reflection or the reflected energy. The other one is that the Schlick approximation is a certain graph. This graph, if you remember aluminum, for example, that is a very slight deviation, but we have other deviations like cloth that the graph looks totally different. Yes, I see that Aaron raised your hand. Go ahead.
Hi, great presentation, by the way. I was wondering about transparency, if that affects the PBR shading, or if transparency is not completely different as a post-operation blending with the background.
Okay, this is actually a great question. So transparency shouldn't, because if we refer to this entire PBR as something which is inherited and every material can be represented with a proper response, then what happens with transparent object is that they're very reflective. And so you represent the media, how the media, you represent this by the Snell, right? So we have N1 and N2, which is the coefficient going between two medias. So this is perfectly represented by the equation. So everything which is not reflected, and reflected, we showed exactly the PBR equation, how to represent this. Everything which is not reflected is now not absorbed. So for real transparent material, we have additional function that we just need to implement, which replaces the diffuse behavior. And instead of just being a diffuse behavior, what will happen now, we will generate a refracted ray, and this refracted ray might generate the same PBR interaction from scratch in the underlying surface. So we will need to gather all the subsurface contribution of energy, but basically it's the same, the exact same PBR interaction, only recursive in depth. So you need to gather the energy that penetrates and comes back.
Yeah, makes sense. Thank you.
I didn't mention also something which is called, well, I will not call it specular. Let's talk about clear coat. So we have something which is called clear coat in our PBR material, and today it's becoming almost a standard. And clear coat is when you take a material and basically you're putting a coat of lac, which basically remains or retains the ability to look through the material, into the material, but really it increases the reflectiveness by much. And so it conceals the normals of the underlayer and a lot of other things. So what we have here is really an interesting phenomena, because what we have here is, in a way, two materials. We have the first material, which is really high reflective, and we can define how reflective it is. And so most of the energy will go on reflection. But the remaining energy, and will be exactly like we discussed, the remaining energy, we said that it will go on the diffuse, right? But in this case, no, it does exactly what we expect from transparency. It will go down, but here the assumption is that it's so thin that it will go down straight at the same point. So this is the only difference. Otherwise, we will need to apply refraction, and refraction will move the point a bit. So in the case of clear coat, we have the main lobe, which is the clear coat lobe. We will compute the specular. Then we will take the diffuse portion, and what we will do with it, instead of just having it as diffuse, no, we will now apply it on a second layer. And there again, we will compute the specular component and the diffuse component. So really, when we have a clear coat, we're computing now three components. We're computing the first layer, the clear coat specular lobe. Then we're computing the second layer, specular lobe, and diffuse. And this is really what clear coat is. And just as a quick reference, let me
So what is the final color then? So you have two speculars and two diffuse. How do we actually merge them for clear coat? So there's a specular, there's a diffuse from the first.
So you add them.
You just add them?
Yes, it's additive, but the way to add them is in a way that you preserve the energy. That means that you use from the first lobe, from the top coat, you're using the clear coat, you're using the Frenet. This will be the coefficient for the specular. Then you're taking 1 minus Frenet plus obviously what we say, the geometry factor missing, and you apply this to everything remaining. But everything remaining is now multiplied by that, which means now you're multiplying the Frenet of the second layer, and this will be the specular, and the remaining of that Frenet is multiplied by the diffuse of the second layer, the inner layer. So this is really what clear coat is. It's really two materials. It's two lobes, but the assumption is that it's sampled at the same point. This is a strong assumption. This is what makes clear coat easy because we don't have refraction. Okay, so I'll show you really a fast demo. This is a demo on a prototype tool that I used to work quite a lot, and I like it because it's so simple to use. So for example, you see here the head. Do you see that, or am I stop sharing now? Do you see the head?
Yeah, I can see it.
Okay, perfect. Okay, so I'll take the metallicness now all the way up. So I took it to 1, and automatically you can see that this is clearly, you can see that this is from something like copper or nickel actually, and you can see that there are spots of something that looks like rust, etc. And this is relatively high reflectance. So the roughness is close to 0. So let's take the roughness up, and you'll see, as you can see, the reflectance immediately controls that. Okay. Now let's take the reflectance back down, just because we're running out of time, and let's play with the metallicness down, and you see that as I go down, somewhere in the middle, it starts to look like it's maybe closer to iron or nickel. If I continue taking it down, then it's becoming more like marble, more like stone. In this case, more like marble, but if I take the roughness up, then it really starts to look like limestone. And the spots there are just spots of dirt. So this shows you the power of just using 2 or 3 textures and some sliders, and automatically you get the right physical response. And by this, I want to stop here because we ran out of time, and I hope that you understood, the bulk of things, 90% of it without getting into the equations, because really I wanted you to understand what this blurb PBR and BRDF is all about, and I hope that I delivered that. Any last question?
I have a quick question actually. So in terms of the BRDF formula, what is the difference in applying this in Atom, where we have real-time rendering, versus path tracing?
Versus what?
Versus path tracing.
Oh, okay. So basically, there's no difference in the equation. The main difference is the way that you gather the energy. So with path tracing, you will shoot as many rays as you need and can support towards the environment. And that means that you need to have a pretty accurate environment, but also as the lobe grows, unfortunately, that means that you need to shoot much more rays to represent that lobe. So this is the main difference. And here, the GPU will really, I mean, even if you send one ray per pixel, this is a cost that today, even with the newest GPU, you cannot do that and have runtime. But definitely, if you start to shoot something like 10 rays per lobe, and this is nothing. I mean, as you increase the roughness, you'll need to shoot much more rays. Even if you have a denoiser, you'll bring the GPU to its knees. So what we're most of the time choosing to do is to use a combination. For example, in Atom, Doug can speak about this, and I actually encourage to do a presentation about this. One of the approaches is to gather through ray casting, gather the probes themselves, and then use the probes just like we seen in this presentation as environment maps, as to say, or GI maps. Okay, guys, we ran out of time and we have other meetings, so I really hope that you enjoyed this. Thank you very much for joining me, and I'll post what is the next presentation next week.
Thanks, Eddie.